Hello everyone, my name is Tracy Pendo Onim and I'm a software engineer building with Elixir. I focus on developing custom software products tailored to client needs, and I also mentor developers to level up their Elixir skills with an aim of helping you to build better scalable applications. Imagine a waiter who never forgets your order and can handle multiple requests at once, all while ensuring every table gets served. Picture this. You are at a restaurant serving, and the waiter takes your order. Now, what if I told you this waiter is the GenServer of your program? Curious? Let's dig in. Here is how it goes. The waiter takes your order, just like GenServer receiving your message. They write it down. That's GenServer keeping track of state. Then they come back to update you. Your food will be ready in 15 minutes. That's GenServer notifying you. And when you ask, is my food ready? The waiter checks the kitchen and responds, just like GenServer sending back the data. Sounds cool? Right. Basically, GenServer is like the waiter in your application. It's efficient in managing requests and keeping state. Here now is the fun part. The waiter can handle multiple tables. That is concurrency in action. So, what is GenServer in Elixir? GenServer, short for generic server, it's a tool that helps you to create long-running processes. These processes are isolated entities that performs a specific action, just like the waiter serving the customer. Now, how can you leverage GenServer in real time? Imagine you want to be sending emails to new users daily at a specific time. GenServer can automate that task for you. Or think of live scoreboard applications. GenServer keeps those scores updated in real time. And of course, you can also use GenServer to create background tasks. There are so many scenarios where you can use GenServer. Think about it. What will you build with a tool this powerful? Drop your ideas in the comment section. I would like to hear them. Here's a question for you. If GenServer is the waiter, what is the kitchen in this analogy? Let me know in the comment section. Stick around and I will show you how to implement a basic GenServer. Welcome back. We have already explored what GenServer is, and in today's video, we are building our first one, our very own customer tracker server. The plan is to track the number of customers entering and leaving the restaurant. We start by creating a new project called Tracker using the mix command line tool. On the terminal, I will write mix new. The mix new command helps you to create a new project, pass the name of the project, which is called Tracker, and add the soup flag. The soup flag creates our application under a supervision tree. We shall explore later what is a supervision tree. Hit enter and our tracker project is created successfully. Once the project has been created, open your editor and let's add a file where we shall build our customer tracker server. I shall add the file under the lib folder and name it customer tracker server. Inside this file, I'm going to create a module using the def module keyword. The name of our server is customer tracker server, and I shall also pass the use GenServer. By passing use GenServer, it will give us access to the function and the callback that are available within the GenServer module. Before we jump into the code implementation, we need to first plan to understand which GenServer functions and callbacks do we need to use. First, what is the initial state of the restaurant? Let's say our restaurant opens at 7 a.m. with no customers. We can have the initial state with customers as 0 and time as 7 a.m. We shall use a map structure to represent the state. At 8 a.m., the restaurant begins receiving customers, possibly 2 or more. The state should be updated to reflect these new changes. Let's take note of the new state. So we can have the customers in the new state as 2 Time is 8 a.m. Our restaurant also has a supervisor who will be inquiring for the exact number of customers in order to assign waiters to different tables appropriately. Finally, we have supervisor inquiry and we need to provide the current number of customers. Now that we have our plan in place, what are the GenServer callbacks that we need? To make this happen, we shall use 3 GenServer callbacks. The first one is the init callback to initialize the GenServer process with the initial state. When customers arrive into the restaurant, we need to update the state. With that, we shall use the handlecast callback. When the supervisor asks how many customers are there, we need to retrieve the current number of customers. The callback that will be responsible for retrieving the current state is the handle callback. Our server has the responsibility of updating the state when new customers arrive and also retrieving the current state. Now, who sends requests to the server? That means we also need to implement the client side to fulfill the client-server interaction. We shall use 3 GenServer functions on the client side. Note that on the server side, we are using the GenServer callbacks. On the client side, we are using the GenServer functions. The first function is the start link. This function will start the GenServer process and also links it to the current process. When customers arrive into the restaurant, the client needs to send requests to the server to add the number of customers to the state. In this case, the cast function will be used to send an asynchronous request to the server. This means that we shall not expect any response from the server. When the supervisor asks for the number of customers, the client needs to send requests to the server to retrieve the current state. In this case, we shall use the call function to send synchronous requests to the server, meaning we shall expect the server to respond with the current information from the state. We are now heading somewhere. We have a clear trajectory of the function that needs to be implemented on the client side and the callbacks that needs to be implemented on the server side. It's also important to note when implementing these functions and callbacks provided by the GenServer, you need to understand the required arguments and the expected return value. Let's start the interactive shell to verify that our code actually compiles before we start implementing the server and the client APIs. To open the interactive shell, run ix-s mix command. We are receiving a warning that the init callback of RT1 required by the behavior GenServer is not implemented in our customer tracker server module. For now, they have injected a default implementation, and this is how their default implementation looks like. We are receiving this warning because we passed the use GenServer in our customer tracker server module. Use GenServer will automatically inject the behavior GenServer. In Elixir, behaviors are like contracts. They ensure that the set of required functions are implemented, and if the defined functions are passed as required by the behavior. That's why earlier I had mentioned that you need to take note of the required arguments and return value expected when you use the GenServer functions and the callbacks. Behaviors are important when modules share a public API. In our case, GenServer serves as the public API we are using. We can now get started with implementing the server API. In the server API, we needed only 3 callback functions, that is the init of RT1 to initiate the process and the initial state. We also need the handle casts of RT2 to update the state, and we need the handle call of RT3 to retrieve the state. Let's start with the init callback. So before we define this callback, let's see what the init callback requires as the argument and what it returns as the expected value. I will head over to the GenServer documentation. Under the GenServer module, we have the callback section. Open the callback section and go straight to the init callback. You can see that the init takes in one argument. This argument can be any term, then returns and a tuple of an atom under state. It can also return a tuple of an atom of state, timeout, or an atom hibernate, or even a tuple of an atom continue and the continue argument. It can also return an atom ignore and also a tuple of an atom stop and a reason. The reason can be any term in Elixir. In our case, we are going to return a tuple of an atom under state. Let's go ahead to define it. This is the init callback. Takes in an argument, then we return a tuple of an atom and the state. We are passing the state as a map structure, and this is how the initial state looks like. For now, let me just pass it as the state. If you're wondering why I passed it as the state, remember when we received a warning? Let me go to this warning. In the warning, they mentioned you can copy the implementation above or define your own that converts the argument given to GenServer start link of RT3 to server state. That means when you call GenServer start link function, it's going to invoke the init callback to initialize the process. This init takes in an argument that is passed to the start link function. That means in our case, when we are calling the start link function, we are going to pass it an argument which will be our initial state. With a tuple of an atom under state return value, our process will be initialized successfully and also the initial state will be set. Next is the handle cast callback. Let's see what the GenServer docs has to say about it. The handle cast takes in two arguments. The first argument is the request and the second argument is the state. The request can be any term and the state also can be any term. Then it returns a tuple of an atom no reply and the new state, or a tuple of an atom no reply, new state, timeout, or an atom hibernate, or a tuple of an atom continue and a continue argument. Also, you can return a tuple of an atom stop, reason, which can be any term, and a new state. In our case, we need to only return a tuple of an atom no reply and a new state. This return value will continue the loop with the new state, and that is all we need to do. Let's define the handle cast. Takes in the request and the state and returns, and we are returning no reply and the new state. Handle cast is the one responsible for updating the state when customers arrive or leave the restaurant. How will the handle cast know that it needs to add customers when they arrive or remove customers from the state when they leave the restaurant? We need to be specific with the request that handle cast needs to handle. If the customers are arriving, we need to tell it that we need to tell the handle cast that it's handling the request of adding customers to the state. So here I'll replace the request with a more specific message, which is add customers. I'm passing it as a tuple, add customers, but it can be any term. You can also pass it as a string the way you wish it. Then it also needs to know that when customers leave the restaurant, it needs to update the state by removing the customers who have left. I'll copy this and paste it, then replace the add customers with remove customers. That way it will know which request to handle. Now, how can it know the number of customers that it needs to add to the state or remove from the state? This information needs to come with the request that it's receiving. So passing it as a standalone atom is not flexible for us, because we also need to know the number of customers that we are adding or removing. Instead of passing it as an atom, I'll pass our request as a tuple. Remember, request can be any term. You can also pass it as a list or a map, the way you wish it to retrieve the information easily. In my case, I'll pass it as a tuple. The first item in the tuple will be add customers. Then the second item in the tuple will be number of customers. The same thing will be done on the other handle cast. I'll just copy and cut this. Now we have the information that we will need to update the state. If you're wondering if it's possible to call a callback, a GenServer callback more than once, the answer is yes. You can call it as long as you pattern match it with how you want to handle it, depending on how you want to handle it. Now we have the number of customers and we need to update it. This is add customer. That means our new state is of a map structure. We need to update the information in the state with the number of customers that we need to add. I need to update the state. I'll remove this. Have our state, and in the state I'm updating the customers. The number of customers is an integer value, therefore I'll do state.customers to retrieve the initial number of the customer number and add that number to the new number of customers that we have. We have updated the customers in the state. We also need to update the time so that we know that at this time we had this number of customers. We have time. With time, I will pass it as a, let me see if I can use time. Which function of time can I use? We can use time UTC now. We shall do the same in the remove customers. I can copy this the way it is and replace the new state with that. But now remember, with the remove customers request, we need to subtract it instead of adding. The final callback we are implementing is the handle call. Let's see how it works. Handle call takes in 3 arguments. The first argument is the request, the second argument is the from, and the third argument is the state. The request can be any term. The from refers to the reference of the process, and the state can also be any term. We already know that our state is a map structure. Then the return value can be a tuple of an atom reply, a reply, and a new state. It can also be a tuple of an atom reply, new state, timeout, or an atom hibernate, or a tuple of an atom continue and a continue argument. You can also return a tuple of an atom no reply and a new state. And also you can have a tuple of an atom no reply, new state, timeout, or an atom hibernate, or a tuple of an atom continue and a continue argument. You can also return a tuple of an atom stop, reason, reply, and a new state, or a tuple of an atom stop, reason, and the new state. We need to retrieve information when we send requests that will be handled by the handle call. Therefore, our return value needs to return for us a reply. In this case, we shall use the first return value, which is a tuple of an atom reply and the new state. Let's define the handle call. Takes in the request, the from. I'll put an underscore to from, and this is because we are not going to use the from argument, and the state. Our return value will be the reply, a tuple of an atom reply, and the new state. But we are not updating the state when sending requests to be handled by the handle call. Instead of the new state, we'll just return the state as it is. What is the request in this case? We want to get the number of customers when supervisor inquires or asks for the customer number. Therefore, our request needs to be specific. We can call it get customer number. Then it needs to send a reply to the caller. And our reply, they mention if the reply can be any term. Yeah, the reply can be any term. We can return the reply as a string, just the way we had mentioned here. We have current customer number, so we need to pass it here. This means I want to interpolate the value that I want to retrieve from the state. Interpolating is like concatenating, so I want to concatenate the string, the current customer string, with the integer value that I'm retrieving from the state. And this is how I can interpolate that value. We have state.customers, current customers number, and add is. Then we can also pass the time. The same thing I will have to interpolate state the time. Therefore, when we want to get customer number, we shall have this information. The current customer number is, and also the time will be given. The server API is completed. We can now move to the client API. Usually it's recommended to define the server API and the client API in different modules. But in this case, I am demonstrating and the application is still small. I will have to define the client API in this module. For the client API, we are using 3 functions. That is the startLink function. We have the startLink, which will start the GenServer process. We have the cast function, which is the one that will be used to send requests to the server to update the state with the current number of customers. Then we have the call function, which will be used to send requests to the server to retrieve the current number of customers. We shall start with the startLink function. Head into the GenServer docs to confirm what the function takes in. So we're no longer using the callbacks. The startLink function takes in 3 arguments. That is the module, the initial argument or the second argument in the startLink. Then we have options, which defaults to an empty list if it's not passed. The first argument is the module. This we can pass as the module that we are currently in, that is the customer tracker server module. Then the initial argument can be any term, and the options needs to be passed as a list if we want to pass the options. First, we'll start by defining a custom function, which will be used to invoke the GenServer startLink. I'll define a public custom function. I'll just call it startLink. Pass the argument as default. This is the custom function. Inside this custom function, we are going to invoke the GenServer startLink function, and it takes in the module name. The module name we can pass as the customer tracker module. You can pass this or copy the exact name as it is. Then the second argument is the initial argument. The second argument, I'll pass it as the argument that we shall pass when we call our custom startLink. Just pass it as default. Remember that this default argument is the one that will be passed to the init callback once we start our server. Therefore, our argument here will be a map structure. If it's not passed, we can pass a default argument. I would prefer we pass a default argument if we don't want to pass anything, and the default argument will be our initial state. I'll just say customer. I'll pass a map of customer 0 and time as time.utc now. That's it for startLink. Next is the cast function. Let's see how it works. The cast takes in 2 arguments, that is the server and the request. It needs to know the server in which the request needs to be sent. Here, the server can be passed as the PID. The PID refers to the process identification, or we can also pass the name of the registered process. When we are calling the startLink, we are not registering our process. That means when we call GenServer cast function, we shall pass the PID instead. Let's define a custom function which we are going to invoke. In this, we can say the cast adds customer and sends request to add and sends request to remove the customers. In this case, I can call it as add customer. This is the custom function. Add customer takes in the server. It will text the server. We shall pass the PID. Then takes in the request. Remember the request that we passed as we're adding customer, which is the tuple. The handle cast expects the request as a tuple of atom of add customers and the number of customers. I've just remembered that this is the function that we need to invoke. I'll just pass this as request because we're calling it. Then this function needs to invoke the GenServer cast for our request to be sent to the server. GenServer cast takes into arguments that is the PID and the request. We also need to define another custom function called remove customer. We don't have to have two functions which are calling GenServer cast. We can only have one. We can name this add or remove customer. Add or remove customer. The function will call GenServer cast, give it the PID and the request that it needs to send to the server. The final function that we need to invoke is the GenServer call. It takes in 3 arguments. The first argument is the server, which I mentioned can be the registered name of the server or the PID. The second argument is the request that needs to be handled by the server. And the third argument is the timeout, which defaults to 5000 milliseconds or 5 seconds. The timeout specifies the time that the call function can wait for the reply. If within the 5 seconds, which is the default value, the call function does not receive a reply, it will time out and also cause the caller process to exit. Let's define a custom function called getCustomerNumber. GetCustomerNumber, which will invoke the GenServer call function. The GenServer call expects 3 arguments, which we have seen is the server and the request. The timeout, we shall use the default 5 seconds. When we call getCustomerNumber, we need to pass it the PID and also we need to pass it the request. GenServer call function will take the PID that we pass that the server needs to handle. Congratulations for the job well done. We have just completed implementing our tracker server. We are now ready to interact with our customer tracker server. Let's test our code in the interactive shell. We already opened the interactive shell. If you closed yours, just call the ajax-smix command again. We made changes to our server module, therefore we need to recompile. Notice that the warning has disappeared, and that is because we added the init callback. We now need to spin up our customer tracker server by calling the start link, which will start the GenServer process. When we call the start link function, it's going to return a tuple of an atom and a PID. That indicates that our process has been initiated successfully. When calling the startLink function, we shall pattern match with a tuple of an atom and a PID. Then call the customer tracker server and pass it the startLink function. If we don't pass any argument to the startLink, the argument will default to what we passed. You can see we have a tuple of an atom and a PID. This suggests that our GenServer process has been started successfully. What is the current number of customers? We can easily check that by calling getCustomerNumber. Customer tracker, we call the getCustomerNumber, which we need to pass the PID that we pattern matched when starting the GenServer. Then the request. So the request that is expected, it's an atom getCustomerNumber. This will retrieve the current number of customers in the state. And we are having an error. Our GenServer has terminated and it's complaining of the key customers not found in the map that we passed. We have a key error, which is the key customers is missing in the map that we passed. This is customers and this is customer. We missed to pass S in our default value that we passed when defining the startLink function. So we can easily rectify that, then recompile our changes. Now notice that which PID were we using. The GenServer PID is 152. This is the process identification of our GenServer. Then you can also see the client PID is this one, which we are told is alive. The client PID in this case is the caller process, which is the interactive shell, which we are using to invoke the functions that we need to send requests to the server. Our interactive shell is acting as the client. Let's confirm if the PID we are told is matching. This PID, at this point, we are told get customer, the state is this, the client PID is alive. This was the client PID at that time. Then when everything just blowed up, the client PID also exited. Here we're told the shell process exited, and this was the previous PID of the interactive shell. What we have here, let me just close this, then call self again. What you have here is the current PID. So when our GenServer process is terminating, the caller process is also affected and exits and restarted again. We have rectified the customer keys that we were passing in the start link. Now recompile the changes, and we need again to start the GenServer process because the previous one was terminated. We have a new PID, that means another GenServer process has been started. Then we can now call the get customer number, give it the PID and the request. And here it is, we have our current number. We are told the current customer number is 0, and the time, this is the time. 2 customers has just entered the restaurant. We need to update the state. The state needs to reflect the customers that have just entered the restaurant. Invoke the add or remove customer, pass it the PID and the request that it needs to send to the server to update the state. Our handle class expects a tuple of an atom, add customers, and the number of customers that it needs to add. 2 customers just entered the restaurant. Remember, with the GenServer cast function, we don't expect a reply because it's sending asynchronous request to the server. Regardless if the request is successful or not, it will always return an atom. To know if the state was updated, we need to call get customer number, and the current customer number is 2, and also the time is updated. Then one of the customer is done with their meal. Now they are leaving. We need to call add or remove customer again. Pass it remove customer, replace the add customer with remove, then remove 1. We have sent request to the server to remove that 1 customer. Now get the current customer number. How cool does it sound knowing that you can build a stateful process that you can interact with? Our customer tracker server is working as expected. Have you ever wondered why some supermarkets seems to be faster at checkout than others? Let's dive into this using Elixir GenServer. When you walk into a supermarket, normally what do? You grab your item, queue up at the cashier, pay, then leave. But how these supermarkets manages their queues can tell us a lot about concurrency. Let's compare 3 supermarkets: Supermarket X, Y, and Z. At Supermarket X, we have only 1 cashier and 2 customers at the queue. It takes about 2 minutes to serve each customer. So the total time taken by Supermarket X to serve the 2 customers will be 4 minutes. At Supermarket Y, we also have 1 cashier, but 10 customers are in line. With the same 2 minutes per customer, it takes Supermarket Y 20 minutes to serve everyone. But what if we had 10 cashiers for 10 customers, or 2 cashiers for 2 customers? In short, each customer with their own cashier. Enter into Supermarket Z. Each customer gets their own cashier. And guess what? Everyone is served within 2 minutes. This ability to handle multiple tasks simultaneously is what we call concurrency. It's like giving every customer at the supermarket their own cashier instead of waiting in a single line. Let's take this concept to an online store, the virtual equivalent of the supermarkets we have just discussed. In an online store, as a user, you are able to browse for the product and place a purchase, and it is at the checkout point where you finalize the purchase and pay for the product. For this demo, we shall simulate the checkout process for supermarket X and supermarket Y, where the task is handled sequentially. To process the checkout, there are information that is required from the user. This includes the customer information like the name, the email, and the address for shipping purposes. Then there's the payment information, which includes the payment mode that the user can select. For example, here I've only provided the phone number. That means that the user can pay through their mobile banking. For example, you can use M-Pesa, or you can use the credit card and the debit card payment modes. Then there's the order summary, which includes the item selected by the user and the total amount supposed to be paid. Our checkout logic will involve saving this information and processing the payment. Let's write some code and see how long it takes to complete the checkout one at a time. This is the checkout module where we are going to add our logic. What we need is to save the checkout details and also to process the payment. Let's define the function for that. I will call it process. This function will take the checkout detail. Inside this, we need to save the information, save the checkout information or checkout details, and also we need to process the payment. I'll define it as a private function, then name it as save checkout details. We need all the information that we get from the client side. This function will not actually perform the actual logic of getting the information and saving it into the database, but I will mimic that process. The saving of checkout details takes 1 second. Therefore, I will delay this process by 1 second or 1000 milliseconds, and assume that we have saved that information. If it's a successful saving, let's just display the information or output checkout details saved successfully. That's it for save checkout details. You can just put an underscore to this. Then we also need to process the payment. Same thing here. I'll just simulate the payment processing but not perform the actual payment. You can just name it as process payment or make payment. The make payment needs the amount. We are providing the phone number. Let's pass the phone number. To process this payment, the checkout application needs to make a request to a third-party API or a payment gateway that will process this payment, then returns back a status if it's successful or not. Let's say that this process takes 3 seconds for the payment to be processed. We can delay that process by 3 seconds using process sleep function. Same thing, we shall output and say payment processed successfully. I will interpolate the amount in here. Payment of amount from the phone number. Let's pass the phone number. Has been processed successfully. So that's it for the logic. Now we need to invoke this function inside the process. We have the checkout details. Another thing, let's just add a status. We can pass a tuple of an atom and maybe say success. And this we can also say an atom of payment successful. Now we can invoke the private functions that we have just defined. I will use the with clause since I want to ensure that the transactions involved are all successful before we complete the checkout process. Let's define the with clause. The first function that I am invoking is the save checkout details. This returns a tuple of an atom and saved status. I'll just copy this. The params here is the checkout detail. The next function to invoke is the make payment. Once the saving of details is successful, we're going to invoke the make payment function. This is the make payment, which takes in the amount and the phone number. If both transactions are successful, we return an atom. Else, if we get an error, we just return that error. The else part is just for the future purpose. We are not handling the third path. The other thing before I forget, we need to retrieve the amount and the phone number that we are passing to the make payment function from the checkout details. This is how the checkout details will look like. I have passed this information under .ix.exs script file, which is defined under the root folder of the project. You will see how this script file will be of handy while we are testing. From the checkout details, we need the phone number and the total amount. To get this information for the phone number, that will be easier. We can do the checkout details and access the phone number. This is one way of accessing information from the map structure. The total amount, we need to go through the items, then through the total. So let's do that. Use the checkout details. First access the items. The items is also a map structure. Then you can access the total. That's it. Our checkout process logic is now completed, and you can see that it will take approximately 4 seconds for the checkout to be completed. Let's test the checkout process and verify that it's working as expected. Spin up the interactive shell using x-smix command. We have our .ix script file, which we added the checkout details. Just write checkout details if you added that file, and you'll see that you have that information. That's why I told you that this file will be of handy. So you don't have to be copying or writing these checkout details in our interactive shell each and every time that we need to use it. Let's call the checkout process function, that is checkout.process file, which takes in the checkout details. Checkout details saved successfully, that is after 1 second. Then after the 3 seconds, we are able to make the payment, and you can see we have an atom being returned, meaning that the checkout process is successful. This is a checkout process for one user. Assuming we are simulating Supermarket X, which was serving 2 customers, let's see how long that will take. But before we do that, let's make some enhancement to our code for the process function to be able to handle more than one checkout details from different users. I'm going ahead to add another function head with the same name. Process will take in the checkout details. To differentiate the 2 arguments, this will be checkout detail to mean 1 instead of details. Then since the 2 functions are similar, the only way to know which functions to call and not conflict, we need to add a guard clause. The checkout details in here will be a list, and this will take in a map. I will add a guard clause for that to pattern match if it is map. Also for this, I can add a guard clause when is list, because we have that. This is when it's map. For the lists, we shall iterate through the list. I will use each for this because the enum each returns an atom, and I don't need the return value or the output. I'm not doing anything with the output, just use enum each. We pass in the checkout details. That is a checkout detail without an s, and for the non-max function must have an end. We are iterating. In here, I will call process function and pass it the checkout detail. This function that I've invoked inside process will match with this one. That's it for this enhancement. Let's also make a change to our IX script file. Instead of checkout details being a map, let's pass it as a list and also pass more checkout details inside the list. For now, we are simulating Supermarket X. Only need 2 checkout details. I will copy this and paste it. Maybe change the phone number for them to be different. This can be 11 and amount can be 1000. We have that. Let's go ahead and recompile the changes and process the checkout for the 2 customers. So just write recompile for it to pick up the changes. We have an error. Undefined variable checkout details in the checkout file line 15. Now it's taking checkout detail and not checkout detail. Let's correct that. We can recompile again. Everything is now good. Let's see how the checkout details look like. It hasn't picked up the changes that we have made in the script file. I was expecting a list of maps and not a map. I think recompiling does not have an effect on this. Instead of recompiling, close the current interactive shell and reopen it. Let's confirm if the changes have been picked up. Now the checkout details is a list of maps. We can go ahead and call the checkout process and pass the checkout details. I had added a printout for the starting time and also for the ending time, to be aware at what time the checkout process started and at what time it ended. If we calculate the difference between the ending time and the starting time, you will see that it takes 8 seconds to process the checkout details for the 2 customers. Let's move to Supermarket Y, which had 10 customers and 1 cashier. I have made some changes in the IX script file. Instead of increasing the whole checkout detail map structure when we need to increase the number of checkout details, I'm using the inner map function to create the checkout details by iterating through a range of numbers 1 to 10 and creating a checkout detail for each number. Then I'm passing the phone number as the number within the range and the total amount as the number within the range also. When we run these checkout details, it will give us a list of the checkout details for each number in the range. Let's confirm that first. This is a list of checkout detail for the number 1 to 10. That way it will make our work easier. Each time we want to increase the checkout details, we just make the changes within the range of numbers that we are passing in the inner map function. Now let's go ahead and see how long it takes to process the checkout information for the 10 customers. I'll clear this. Then I need to call the checkout process. You can see the starting time is 7:20. This is the starting time. You can see it's processing one at a time. We are at the 5th checkout. Let's just give it a few seconds to complete. It has completed, and this is the end time that we are having. Let's get the difference between the end time and the starting time to see how long it took for the checkout to be completed for the 10 customers. I'll just replace this with the time we have, then copy the start time. It took 40 seconds to process for the 10 customers. As expected, serving the customers one at a time gets slower as the number of customers increases. When we served 1 customer, it took 4 seconds. When we served 2 customers, it took 8 seconds. When we increased the number of customers to 10, it took 40 seconds for the checkout process to be completed. That does not sound ideal at all. What if we could make this process to be faster? Stay tuned for part 2, where I will introduce concurrency to our checkout process. If you're curious how concurrency works in Elixir, you don't want to miss the next video. Do you remember Supermarket Y, where we had the checkout process taking forever because customers were being handled one at a time by one cashier? On today's episode, we shall actualize Supermarket Z concurrency magic with Elixir GenServer. First, let's have a quick look at our current checkout process. With the current setup, each checkout detail received is being handled one at a time. It takes 4 seconds to complete one checkout process. 1 second is for saving the details into the database and 3 seconds for processing the payment. Just like Supermarket Y, it works, but it's slow. If you are processing 10 checkouts, it will take 40 seconds to complete. So let's run the checkout process and see. So that is the model name, and I call the process function, which takes in the checkout details that were already added to the EX script file. If we run this, we shall see some of the information printed on the screen. We shall know the starting time and the time it took for all the checkout details to be processed. And also we shall see the difference between the end time and the start time. I'll run this. So remember, it takes 4 seconds for each checkout to be processed. And say after the 10th checkout process, we can see the total time taken is 40 seconds. To fix this, we shall use GenServer to create isolated process for each checkout request received. The aim is to build a checkout process that is fast and efficient. This way, we are guaranteed that tasks will run concurrently, just like having a cashier for each customer. Let's get started with implementing a GenServer that will be responsible for each checkout request. Therefore, I'm defining our server as checkout server, that is dev module checkout server. Within our server, we'll need to have access to the GenServer callback and functions. Therefore, pass use GenServer. Within our checkout server, we need to know which callback and GenServer functions to implement. The first callback that we shall implement is the init callback of RT1. If we fail to define this callback function, we will get a warning that it's required. This is on the server side. On the client side, the function we need is the startLink function. This is the function that is responsible for starting the GenServer. Let's start with these two first, then we move to the next step. We can start with the startLink function. That is the client side. I'll define a startLink custom function. This is a custom function, not from GenServer, which will take one argument, then invoke the GenServer startLink function inside this. Startlink is of RT2. It will take in the module name. Let's start with the startLink function, which is on the client side. I'll name the custom function as startLink. Takes in an argument. Then inside this function, I will invoke the GenServer startLink function, which takes into argument the module name. Then you can pass the argument here. So this argument will be the one passed to the init callback function once the GenServer process has been initiated. On the server side, we are adding the init callback. Let me remove this here. Have the init callback. The init callback takes in one argument. This argument is the one that is coming from the startLink function. I'll call it state, and we shall return an OK state. By returning an OK state, you are declaring that once the GenServer process has been started and the init callback returns an OK state, that means that the GenServer process has been started successfully. We can start our server and see if up to this point it's working as expected. Spin up your server by running ix-smix command. Check out server startLink function that I've defined. Pass in any argument, even if it's an empty list. And yes, we have managed to start the GenServer process successfully. You can see we have an OK and a PID. So this PID is the process identification of the GenServer that we have just started. The next step is to customize our checkout server, start a process to be able to start a unique process for each checkout. We shall do that by registering our GenServer with a unique name. And to register the GenServer, we shall use the name option, which we shall pass as a third argument to the startLink function. You can pass it as one and try it out. Recompile the changes, then restart the GenServer process. And we have a problem. We have an argument error, expected name option to be one of the following, either nil, atom, or a global term, or a tuple of an atom via module and a term. But we passed a string. It does not take a string as the name. I'll change this to an atom. Let me pass it as one. I'll then recompile the changes again and restart the GenServer process. We have been able to start the GenServer process, and the name that we have registered it with is an atom1. Let's see the process info. I'll pass it the PID. I did not pattern match. I could easily retrieve that info. Oh, I can't retrieve it. Let me try to retrieve the PID. So we have an OK PID, and I'll call the X that was responsible for it, that is V4. Now I have the PID. Let's check the information of this process, and you could see that the process has been registered with the name of an atom1. We are on the right track. Since we are starting a GenServer process for each checkout, our argument can be the checkout details, and we retrieve the name from that information. Let's see how the checkout details look like. This is the checkout details, and the only unique thing here is the phone number. Let's add an ID here, and this ID will be the number for each checkout detail. This is X. I'll pass the variable X. So with the ID, we have a problem. I'm trying to see if it's possible to convert a string number into an atom, which I don't think is possible. We can try that. String to atom, and I pass it a string 1. I don't think this will work as we intend it to work. In our case, this name needs to be unique to be able to start a GenServer process for each checkout. I have decided to pass the literal string within the inner map, and each value within this list will be passed as an ID and converted to an atom. We can now go ahead and retrieve the name from the argument, which we know is the checkout details. Actually, we can retrieve it by calling ID. What if the argument is an empty map? Which you can make the argument default to an empty map. If an argument is an empty map, the name will be nil, and that will also be a valid argument. There's no problem. Now that we know that the argument is the checkout details, let's go ahead and retrieve the name. To retrieve a value from a map, we shall do argument and access the ID value. We can recompile the changes and see if this actually works. I need to restart the IEX because we changed the IEX script, and for it to pick up the change, I need to restart it. Let's see what we have in our checkout details. The ID has been updated as expected. Let's start a GenServer process for each checkout. I've closed the IEX. That will be fast. I'll do inner map. Actually, let's just start for 3. I just need checkout details information and see which one I can use. Let me copy paste this. Checkout 1. We have that. Then let's call the startlink function, the server startlink function, which takes in the checkout details. We have been able to start the GenServer process, and you can see it has returned an OK and a P. Let's check the information of this process. And again, I forgot to pattern match. That is v3. To check the information, I will call process.info function and pass it the PID. You can see the registered name is 1, and that is what we have as an ID. Let's do another one for checkout detail ID 2. We can do for a random number, even 6. Checkout, this is 6. Paste that. And then let's call the checkout server startlink function and pass it the new checkout detail. This is another server started. I keep forgetting to pattern match. Pardon me for this. This is from IX8. Let's see the first PID we had. That is 402. And this one is 404. Let's check the process info of the new GenServer process that we've just started. Give it the PID. And you can see the registered name is 6. This way you have been able to register each GenServer process with a unique name. The checkout server will be the one responsible for saving the checkout details into the database and processing the payment. We need to make changes within the server. In the init callback, instead of returning a tuple of an atom and a state, we can add a third value within this tuple, which is a tuple of an atom continue and a continue argument to be able to perform a post initialization task. That is a task that is done after the GenServer process has been initialized. Have an atom of continue and a continue argument. So the continue argument can be anything, and what we want to do is to process, can be any term, that is we want to process the checkout. Just call it process checkout. If we run these, recompile the changes first, then let's start the GenServer process. The GenServer of checkout 6 was already started. I'll need another checkout detail. I can copy paste this, maybe 7. I'll need a way to change this name. Let me just change it from here. This is 7. I want to try out the new change and see. Checkout 7. You can start a new checkout process called startlink and pass checkout 7. This is a new GenServer process, and we have an error, and the function that is undefined is handle continue. This error takes in process checkout. This is the continue argument that we have passed in the init callback as the return value. This is the state. You can see it looks similar to checkout 7. Let's see the ID and confirm. This is checkout 7. Then it only have 2 arguments, the continue argument and the state. Therefore, we need to also define the handle continue callback within the checkout server. Let's define the handle continue callback. takes in the continue argument, which is the process checkout. The state is our checkout detail. Then for the return value, we shall pass no reply and the state. It's within the handle continue that we're going to save the checkout details to the database and also proceed with payment processing, similarly to what we were doing here. Therefore, I'll just copy this as it is and paste it the other side on the server side. Also, we need to copy the private functions involved. I'll cut and paste it here. Now let's see what we have. Replace the checkout with the state. Also, I was thinking, since we are starting a GenServer process for each checkout received, instead of leaving the GenServer process idle after it has completed its task, we can terminate or stop that GenServer process from running. Therefore, instead of returning a no reply state in the handle continue callback, I will replace this with a tuple of an atom stop, pass the reason, normal, and the state. This way, after the task is completed, it will stop the GenServer process from running. I don't see any other change that we might need. Now we can be ready to spin up our server and see if it's working as expected. Before we do that, there are some changes we need to make within the checkout. This is the process. When the checkout detail is a map, it was the one responsible for saving the detail and making the payment. Now we need to replace this. Here is where we are going to call the checkout start link function and pass the checkout detail. That's it. Now we're ready to test our new implementation. Remember, with the sequential checkout process, it took 40 seconds to process 10 checkouts. Now let's see how long it will take. Let's open the IES. I'll have to recompile for the new changes to be picked up. We are good to go. The checkout details, I think this is intact. Now we are not calling checkout start link function directly. We shall use the client side. We shall use the checkout process function, which takes in a list of checkout details. So that is checkout. I should have renamed this model to checkout client. Let me just do that right now. Checkout client, just to be easier to differentiate. I'll have to recompile again. Call checkout client and checkout client process function and pass it the checkout details. We have called IO puts, which will print the information. This was not supposed to be ending time. Let's change this to time taken. I think it's clearer that way. Compile, checkout process, checkout client dot process, and pass it the checkout detail. Then you can run that. Have you seen what just happened? Starting time was at 5:54, end time at 5:54. Time taken 0. Have you noticed how much faster the checkout process is now compared to how it was before? You can see the time taken is 0. So this is in seconds, and because the default unit for time diff function is in seconds, we can change that to milliseconds and get the actual difference, because there's a difference between the starting time and the end time. Let's update that in here. We can pass the unit as milliseconds. Recompile the changes, then call checkout client process function. We have a warning, deprecated time unit milliseconds. A time unit should be second, milliseconds. I've just added an S. Let's change that. I'll recompile the change and then call the process function again. Even in milliseconds, the time taken is 0. Do I need to change to microseconds? But there's a difference. There's a tiny difference between the starting time and the end time. It's much faster compared to the sequential process that we had before. I have just realized that we are not capturing the correct total time taken. And this is because the time indicated here as the time taken is the total time taken after each process has been started. Actually, what I want to do is to increase the sleeping time to 1 minute instead of 4 seconds. Then I will check this against my system clock. So after the last printout, because we have the printout, you can see the printout after the payment has been made for each detail. After the last printout has been made, I will compare the starting time and the end time using the system clock. I have lost ideas of how I can validate actually, because we are starting a process for each checkout, and if I try to validate the time, I'll be validating for each checkout and not for the total processing time. Let me start the server and call the checkout client process function. Pass it the checkout details. Yeah, it's 9:34. Let me run it. So remember, each checkout is now taking 1 minute. It takes 10 seconds to save the details and 50 seconds for each checkout. Now it's 9:35 and we have completed for all the 10 checkouts. That means it takes 1 minute to process 10 checkouts. If it was for the sequential method, one checkout takes 1 minute. That means it will take 10 minutes to process for each checkout. With the updated implementation, we are able to handle the checkout process independently and simultaneously, and that's why it took 1 minute to process 10 checkouts. That is the power of concurrency in action. Imagine having a restaurant with different departments: the kitchen staff department, which includes the chef, and the waiters department. Who is there to ensure that everything runs smoothly within each department? Of course, it's the manager. Similar to the restaurant work setup, Elixir has an inbuilt tool called Supervisor, which are responsible for the processes assigned to them. The waiter and the chef in this analogy are the processes that are started under the supervision of a manager who is the supervisor. In today's video, we shall explore why Supervisor is an essential tool in Elixir. Back to our restaurant with two departments, the kitchen department and the waiters department. For this restaurant to run, these two departments needs to have staff who will be performing their specific role. The chef in the kitchen preparing food and the waiter serving the customers. I have a question for you. Who do you think will be responsible for hiring this new staff and assigning them their role? You are right, the respective department managers. In Elixir, the supervisor tool works in a similar way. They can start a new process which will be responsible for performing a specific task. Just like the manager in the restaurant, hiring a new chef who will be responsible for preparing food in the kitchen, and a new waiter who will be serving the customers. What happens when things go wrong? Say the chef suddenly leaves in the middle of a client order. This will definitely create a critical situation. The client might be angry when they find out and create a chaos, or even decide to leave, and that means a loss to the restaurant. In such cases, it's the manager's job to ensure that the restaurant is running smoothly. They can decide to hire a replacement if needed. This is exactly how supervisors in Elixir work. If a process crashes, they restart the process, ensuring that the system continues running smooth. In the kitchen, chefs typically works on preparing different meals at their own station. Let's say one chef focuses on grilling and the other chef focuses on preparing a dessert. If something goes wrong with the chef who is grilling, let's say they accidentally burns the food, that should not affect the workflow of the chef who is preparing the dessert. The manager can step in and handle the situation with the grilling chef without even affecting the dessert chef. What has just happened in this scenario is that we have been able to isolate the problem of the grilling chef from affecting the other chefs from performing their task. Let's look at how the concept translates to Elixir. In this diagram, we have two processes, process A and process B. Both of these processes are managed by a supervisor. If process A encounters an error and terminates, it is the job of the supervisor to ensure that the error does not propagate and affect process B. How is this possible with the supervisor? The supervisor process is configured to a trap exit. This is a mechanism that allows the supervisor to acknowledge the exit message from a process that has been affected while they continue to run instead of it terminating. With the trap exit mechanism, the failure of one process is prevented from impacting the other process, and this is because the supervisor that is managing all the processes is still running despite the failure of one process. Remember the basic GenServer we had implemented. We encountered an error, and the error associated to this GenServer process also caused the interactive shell to terminate. Why was the interactive shell also affected? This was because when we started the GenServer process, it was linked to the caller process, which is the interactive shell. And since the GenServer process was not configured to a trap exit, neither was it started under a supervisor, its crash propagated to the caller process. If we had started the GenServer process under a supervisor, the supervisor would have acknowledged the exit of this GenServer process and restart it. This could have spared the interactive shell from being affected by the crash of the process. And that's the power of supervisor in Elixir. To recap, we have mentioned 3 features of a supervisor that makes it a crucial building block for designing fault-tolerant and robust applications. Supervisor can start a process to get your system running. It can restart a process if something goes wrong within that process, keeping your system running smoothly. It can isolate crash, and this ensures that a problem in one area does not affect the entire application. Thank you for watching. Until next time, keep coding and keep building resilient applications. Next, we shall build our GenServer process under a supervisor. In our previous video, we explored 3 key features that make the Elixir supervisor essential for building fault-tolerant and robust applications. In our previous video, we explored 3 key features that makes the Elixir supervisor essential for building fault-tolerant and robust applications. We mentioned that a supervisor can start a process, can restart a process in case of a crash, and can isolate a process that has been affected so that it doesn't take the whole application down with it. In this session, we are going to see the supervisor in action. Remember our customer tracker server, the GenServer process that we created to track the number of customers who are entering and who are leaving our imaginary restaurant. So today we are going to assign it a manager who is the supervisor. Let's start by first understanding the diagram presented here. This diagram represents a supervision tree. At the top of the supervision tree, we have the supervisor process. Under the supervisor process, we have 2 child processes, process A and process B. These 2 processes are managed by the supervisor process, and this is exactly what we want to achieve. We want to start a supervisor process that will supervise 1 or more processes. We can now spin up the interactive shell under the tracker application and start the supervisor process that will be responsible for our customer tracker server. So I'll just write ix-smix command. We are going to start the supervisor process directly using the supervisor start link function of RET2. This function takes in 2 arguments. The first argument is the children, and the second argument is a list of options. The list of children that we are passing to the start link function as the first argument defines the child specification that describes how the supervisor is going to handle the child processes. This is how it describes how the supervisor can start the child process, or shut down the child process, or restart the child process. The child specification is passed as a map format, and it contains 6 elements or 6 keys. That is the ID, the start, the restart, and the type key. But only 2 of the keys are required, that is the ID and the start. We are going to define our child specification using those 2 required keys at the moment. Let's define the child specification. I'll pass the variable children here, which is passed as a list. So inside the list, it's where we're defining the child specification. I will use only the ID and the start key. So the ID is the unique identifier that the supervisor will use to identify the child process. We can pass this as the customer tracker server module name. The second key I'm passing is the start key. This is the key that will help the supervisor know which child process to start. It's passed in a tuple format. Inside the tuple format, it takes in the module, the function, and the argument element. The first element we are passing is the module. So we intend to start the customer tracker process, and to start it we need to call the start link function inside the customer tracker. That is the customer tracker server. The second element is the start link, and the third element is the argument. We can ignore the argument now because if we don't pass, it will still default to the argument that is passed inside the start link. Pass an empty list. The second argument that we are passing to the supervisor start link function is the list of options. In the options, we have the strategy option. The strategy option is the one that tells the supervisor how to manage the failed process. This includes the one-for-one strategy. The one-for-one strategy, if a process fails, the supervisor only restarts that process that has failed. Then we have the one-for-all strategy. In this strategy, if a process fails, the supervisor will restart all the processes, including the ones that are not affected. For example, if we have process A, process B, and process C, and process B fails, the supervisor restarts all the processes here, process A, B, and C. Then we have the rest for one strategy. In this strategy, if a process fails, let's say process B, the supervisor will restart process B, the one that is affected, and also restart the rest of the process that follows after process B. If we have process A, B, C, and D, and process B is affected, the supervisor restarts process B and also restarts process C and D. The second option we have is the max restarts. This defines the maximum number of restarts that is allowed in a given time frame. The default maximum restart number we have is 3, and this is where we also need to be careful when defining a GenServer process. Let's say, for example, we have a GenServer process that keeps on terminating, and this GenServer process is supervised by the main supervisor of the application, which also supervises other processes. If this GenServer process keeps on terminating and the supervisor keeps on restarting this process, once the max restart is exhausted, the supervisor can also be terminated. And if the supervisor is terminated, that means all other processes will be affected and the whole application will go down with it. The other option we have is the max seconds. This is the time frame in which the max restarts applies. It defaults to 5 seconds. Then we have the name option. This is the one that you can use to register the supervisor by giving it a name. Among the options that have been mentioned, only the strategy is required. Now let's go ahead and start our supervisor. To ensure that our supervisor has started successfully, I'm pattern matching with an OK PID as the expected output. Then we call supervisor start link function, pass it the list of children that we have just defined, and also pass the strategy option. So we are going to use one-for-one strategy. We now have our supervisor started. Let's investigate what's happening within the supervisor. We're going to use the process identifier for the supervisor, that is the PID. Let's call supervisor count children function and pass it the PID. It has returned a map which has some information within it. The number of active children within the supervisor is 1. The number of workers is also 1. So the worker here refers to the child process, which is the customer tracker server process. The number of child supervisors supervised by our supervisor is 0. There's no child supervisor. And the number of specification we have, this includes the total count of children within our supervisor, that is the specs. It's also 1. This one refers to the customer tracker server that has been started under our supervisor. We only have one process under our supervisor. Let's investigate further to see if you can get more information about this supervisor. I'm trying to see if we can get the information of the child process started by the supervisor. Let's use the which children and also pass it the PID. Yeah, we now have at least more information about it. You can see the information of the worker that has been started under the supervisor, and also we have the PID of the customer tracker server process. I'm going to define this PID of the worker. Let me call it worker PID. I just want to get hold of this PID and see if we can perform some tasks within it. Call the PID kernel function, pass it 0, 146 and 0. Yeah, so we have gotten hold of that PID. Now, if we want to add a customer, I can call the add or remove customer function. Let me take the customer tracker.add or remove customer, pass it to the PID, then the request message that the server will listen to. This is the request message. The number of customers is an integer number. We can add maybe 3 customers. Something is wrong within our server. No function clause matching in supervisor handle cast. The state, this is the PID of the customer tracker or the... I have passed the wrong PID. The PID I've passed here is the supervisor process and not our worker PID. The other thing you can notice here, I've introduced a crash. I want to see if our worker process is still alive. That is the worker PID. It seems not to be alive. The interactive shell has been restarted. I will need to start the process again, the whole process. We now have the PID of the child process. Let's see if we can interact with it. What I will do is add or remove the customer within our customer tracker. Call customer tracker, add or remove customer, pass it the worker PID, then the message, the request message that the server is expecting. This is the request message, that is add customer and pass it an integer number, or maybe pass it a number 3. We have added the customers. Let's see if it's actually added by retrieving that information. We can retrieve by getting the number of customers. Call customer tracker server and we call the function get customer number. Then pass it the request is expecting, that is get customer number. This function is get customer number or text in the PID. I've passed it with an arity argument, that is the worker PID, and you can see the information being displayed here. Current customer number is 3 and the time is that. That means our child process was started successfully by the supervisor. What will happen if we introduce an error within our server? In this case, we're expecting the supervisor to restart the child process that has been affected. Let's say if that will be the case with our demonstration. Demonstration can also go in a different direction that we don't expect. So let's say if that will happen. We already have our worker PID. In here, an error will be raised. I've just called raise with an intentional error. I want to see if that will be the case or I will have to restart it. I'm going to add customers. Maybe change that to 1. When it's trying to handle the add customer requests, it's going to raise an error. We have an error raised, and here you can see the PID 0158.0 terminating. Let's confirm if that is our worker PID. That is our worker PID. We have a runtime error and has been raised at line 25. That is the same place that we have introduced the error. I want to see if there's any child process that is under our supervisor that is active, and also I want to see if this worker PID is still alive. I don't expect it to be alive. By the supervisor restarting a child process, it means it's starting a new process. Let's see if this is alive, which I don't expect it to be alive. That's okay. Now let's see if there's any child process within our supervisor by calling supervisor. This seems like a long process. Let me just type it. Supervisor count children and pass it the PID. The PID here is the supervisor PID. We have 1 active children, 1 worker. So if you have 1 active child, this means that there is 1 child that is alive. Let's see the new PID of the child process that has been started by calling the supervisor which children. Just pass it the PID again. We have a new process that the supervisor has started. It's working as we expected. Now let's see the isolation in action. What I want to do is start 2 child process under our supervisor. So we are going to start a new supervisor with 2 child process. I want to clear this. I'll define a new child specification just with the same format, the ID, but now I want to use an ID that will differentiate the 2 children. Maybe let me pass an atom. Then use the start. We are starting the customer tracker process. I'll just call the start link function again, pass it the default argument. So that is the first child specification. Add another one. This will pass with an ID 2. The same thing because it's the same. We are passing the server but with a different ID that will differentiate between the two child process. That is the start link. And then the arguments. Here we have that I've closed. I need to close the first map of the child specification. No, that's okay. I can go ahead and start the supervisor. There's a start link function. Pass it the new list of children and the option. If you don't pass the strategy option, it will raise because it's a required option. That is 1-for-1. Now we have started a new supervisor with 2 children under it. Let's get the PID of the workers. We can do that by just using the function with children, then pass it the PID, and we have them here. We can call it worker PID1. I'm just using the kernel function. And then let's have the worker PID 2. That is 174. I want to interact with the first worker, which definitely will fail because of the raised error. Then see if the second worker will still be alive. Let's do that by calling the customer tracker server and add or remove customers. Pass it the worker PID1, then the request message, that is add customers. Replace this with a number, maybe 4. This is worker PID1, which is going to have an error. So we don't expect the worker PID1 to be alive. We expect that the supervisor might have restarted another child process to replace the first worker. And we expect the second worker to be alive. Let's see if the second worker is alive, because the supervisor has the ability to isolate crash. Worker PID2. It's still alive. That means that our supervisor has been able to isolate the crash. What has happened to the first process has not affected the second process. We can also check how many child processes are alive within our supervisor. You can use the count children to check that. We have 2 processes that are alive. Let's see which children are under it. We have 2 children, and you can see that we have now a different PID from what we had with the first child process. So this is another process that has been started. The ID that we passed still matches what we had defined in the child specification. In every Elixir application, there is the application.ex file. In this file, we have the main supervisor already defined for you. If you check in here, we have the start function, which takes in the 2 arguments, and inside it we have the children, which expects the child specification to be passed inside the list. And we have the option where the strategy of 1-for-1 is passed. And also the main supervisor has a name registered for it, which is the tracker supervisor. When you start your application, the supervisor start link function is going to be invoked, and it will start the supervisor, and the supervisor will in turn start the child under it. Let's start the main application and then investigate the main supervisor. We have started our application by just calling ax-sme. Then we can check the information within the main supervisor. Let's call which children to see if there are any children, though we don't expect any child to be started by the main supervisor. It's empty. If we call count children, you can see that there is no active child process, neither there is no worker, there are no supervisor child process. The specs defines the total count of processes under the supervisor. The count is still 0. In our first example, we started the supervisor directly by calling the supervisor start link function in the interactive shell. You can also start a child process by passing it as a child of the main supervisor. To start the customer tracker server under the tracker supervisor, we can specify it under this list. Just call the customer tracker server here. You can pass it as a tuple of a module and the arguments, and also you can pass it as a map format, the way we defined the child specification earlier. So I'll just pass it as a module. For the changes to be picked up, I will have to restart the interactive shell. Again, we can now investigate the tracker supervisor to see if it has a child process under it. I'll just call which children and pass the tracker supervisor. You can see it has one child process, and this is the PID of our customer tracker process. To recap, we have been able to start our supervisor directly by calling the supervisor start link function. We have also seen the supervisor in action, how it can start a child process, how it can restart a child process in case of a crash, and how it can insulate a crash from affecting another process. We have also seen that it's possible to start a child process under the main supervisor by just passing the module name under the children list in the application.txt file. In our next video, we shall look at other types of supervisors that you can define in your application, that is the module-based supervisor, the dynamic supervisor, and the partition supervisor. Previously, we had looked at how to start a GenServer process under a supervisor, and we discussed two ways of doing that. We directly called the start link function of RT2, which took in the list of children that was intended to be started under the supervisor. The other way was passing the GenServer under the application supervision tree. Aside from the built-in supervisor, there are also other ways in which you can create a supervisor, and in this video we are going to look at the module-based supervisor. With module-based supervisor, you are going to define your own supervisor module. Setting up a supervisor module is very straightforward. Let's go ahead and define one. I'll start by defining a file for our supervisor. I'll add it under the lib folder, but inside the gen demo where we have other gen servers defined, I'll call it the tracker supervisor. In the supervisor documentation, we already have a module-based example supervisor which is defined there. So I'll just copy and paste this, then customize it to our liking. That is changed. Then I need to change the children that I'm passing here is the customer tracker, and I'll just delete this so that we have an empty list. In the tracker supervisor, we have the use supervisor. This defines the supervisor behavior and allows access of the callback and the functions of the supervisor. It also automatically defines a child spec. That means if our tracker supervisor is passed under the application supervision tree or in another supervisor as a child of that supervisor is able to call the tracker supervisor child spec with the child specification defined. Then we have the supervisor start link function of RT2, which is defined under the start link. So when the start link function is invoked, it's going to start the supervisor. So this function takes in a module name, the initial argument, and options. The option passed here is the name, which is going to register our tracker supervisor with its own module name. The initial argument that have been passed is the one that is going to be passed to the init callback when the supervisor is started. Finally, we have the init callback. This is where the children that are intended to be started under the supervisor are initialized. So you can see the list of children that are defined here, and we want to start the tracker server under the tracker supervisor. We pass it as a child with a tuple format. Then at the end, we have the supervisor init function of RT2 that is invoked. So this is the function that is responsible for initializing the children. It takes in the list of children and a keyword list of options, and you can see we have the strategy 1-for-1 which is passed. The tracker supervisor is ready to be started, and we are going to start it in two ways. We can start it by calling the tracker supervisor start link function, or we can also start it by passing the tracker supervisor to the application supervision tree. So that means when you pass it to the application supervision supervision tree, it's going to be started as a child of the main supervisor of our application, and it's going to be started when the application is running. Let's start it by manually calling startLink function, spin up the interactive shell, and call the tracker supervisor startLink function. We don't have to pass it anything, but we did not pass any default, so just pass an empty list for now. We can also pattern match it with an OK PID. This PID will be the PID of our tracker supervisor. We can go ahead and check the process info and just validate. This is the tracker supervisor that has been started. Pass it to the PID and let's see. You can see the registered name is the tracker supervisor, so that means our tracker supervisor has been registered with its model name. And we also have extra information in here. It's trap exit. We have the links, so these are the other process that are linked to it. That's how you can start it. You can start it manually by calling the startLink function. Now let's go to the second option. I will have to close the interactive shell because we have to pass the tracker supervisor to the list of children in the application. Let's pass it here. Remember the different format of defining the child spec. You can define it in a tuple format, the way we have passed the customer tracker server here, or you can pass it as a model name, or you can pass it in a map format. The map format mostly is not recommended because it's prone to many errors. Mostly pass it as a tuple, or so as a tuple it's only the model name and the argument or the option that will be passed when the startLink function is invoked. And as a model you just pass the model name, so I'll just pass the model name here because we don't have any argument that we need to pass within the supervisor. When you pass it this way, the supervisor is going to invoke the tracker supervisor child specification and define the child spec function, which has the child specification defined in a map format. That's it. So we have passed it there. Let's start the application by just calling the ix mix file. Don't have much information here, but I will have to retrieve those information. Our supervisor is registered under a name. We can check if we can use that name to validate if this tracker supervisor is started. Actually, we have the supervisor which children of RET1 function, which takes in the supervisor, that we can use to check the children that has started under the main supervisor. Let's look at the registered name of our supervisor here. The registered name of the supervisor is GenServer. We can go ahead and use the supervisor which children function and pass it the GenServer name, and yeah, we can see, so here you can see we have the tracker supervisor which is started under the main supervisor, and that means it's running, and it's running with this PID. You can also validate that it's PID by calling the PID function, pass it 04440. If we check the process info of that PID, everything matches with the tracker supervisor. You can see the registered name is that, and that's the other way you can start the supervisor. When is it useful to define the supervisor module? When you want to increase the fault tolerance of your application. Let's say, for example, you're working with multiple workers or process like the GenServer, and for this process you pass it under the list of children in the main supervisor of your application. In the scenario where one of the child process keeps on terminating, it will be a threat to your application. And this is because the supervisor, which is the one responsible for restarting that child process, each time it terminates, it will get exhausted at some point. And this is because of the max restart option, which once that number is exhausted or is exceeded, it's going to affect the supervisor by terminating it. If the main supervisor gets terminated, all the other children that was started under it are going to be terminated as well. This means the whole application is definitely affected. That's it for this video. To recap, we have defined our own module-based supervisor, and also we have seen different ways of starting it by calling the startling function directly through the interactive shell, and also we have started it by passing it under the application supervision tree. You can also pass it under other module-based supervisors that you define, and this is mostly useful when you want to increase the fault tolerance of your application, and mostly when working with multiple processes or multiple workers. In our previous video, we looked at the module-based supervisor, and we were also able to set up one for ourselves. With the supervisor module kind of setup, we had to predefine the list of static children that are to be started when the supervisor starts. What if you want to start a child process later on, but not immediately when the supervisor is started? What if you add a child to the main application supervisor and that process ends up running idle, consuming memory unnecessarily? What if you are handling a dynamic processing, such as processing transaction during checkout, where the number of child processes that are to be created depends on the users performing the checkout? This is where the dynamic comes in handy to answer those what ifs. Why would you want to use a dynamic supervisor? A dynamic supervisor is started without any children predefined. Therefore, with dynamic supervisor, there is low chances of having idle processes running that will consume the memory. With a dynamic supervisor, children are started on demand, that is, when they are needed. Not having to predefine the children to be started under the supervisor, with the dynamic supervisor, it means that you can start those children dynamically. That said, let's see how a dynamic supervisor works. We shall go through a basic example of a dynamic supervisor. Let's follow this documentation to define our dynamic supervisor. So I want to add a dynamic supervisor under the children of the main application supervisor. So the first thing, let's copy this. Let's add it here on the Gen demo application. So this is the main application supervisor. I will pass this under as a child of the main supervisor. Okay, cursor is there to save the day. What else is missing? So I need to also change that. Okay, I'm having an error I could not figure out. So this is comma, then what else? Okay, so I have defined that. Okay, so the error is gone. So this is our dynamic supervisor. So I've passed this dynamic supervisor, the name of the dynamic supervisor, which is Gen demo dynamic supervisor, and the strategy 1-for-1. So the strategy means if one child process is affected, it's only that child that will be restarted. So dynamic supervisor only supports 1-for-1 strategy. Here we are told once the dynamic supervisor is running, we can use it to start children on demand. So let's start our dynamic supervisor by first spinning up the main application. We shall do that using the ix-smix command. Then let's confirm that the dynamic supervisor is actually running. We can use the supervisor.whichChildren function, which takes in the name, the registered name of the main supervisor. So the registered name is Gen demo supervisor. So here you could see that we have the Gen demo dynamic supervisor, and this is its PID. You can also confirm if it's actually alive. So I will use the PID kernel function to get access of the PID, because I cannot use it in this format, so that's why I have to redefine it. Okay, so we have the PID. Let's use the process.alive function, pass it the PID of the dynamic supervisor, and it's truly alive. Let's go ahead and start a child process under the dynamic supervisor using the start child function of RT2. We shall use an existing GenServer that was initially defined, that is the customer tracker server, So this is the child that will be started under the dynamic supervisor. We shall use this function. Let's see how it works. It takes in the supervisor and the child specification. If we look at the documentation example, so this is the name of the registered supervisor. In our example, we are going to use the GenDemo dynamic supervisor. Then this is the child specification, which includes the child that is to be started. So here a tuple of a counter and a number 0 has been passed. So counter here means this is the GenServer that has been defined. GenServer defined here is called counter. Then 0, this is the initial argument that will be passed when the GenServer startLink function is called. Let's go ahead and define ours and start our dynamic supervisor. So we have the ix-is mix command. So I am restarting the interactive shell. Then we have the dynamic supervisor. We are calling the start child function, which is going to start our customer tracker. Pass it the GenDemo.dynamicSupervisor. Then pass the child specification here. So remember, the child specification has different format. You can pass it as a module, you can pass it as a map, or you can pass it as a tuple. Since I'm not passing any arguments, that will be going to be passed to the startLink function. When it has been started, I'll just pass it as a module. So I'll copy that. Then let's start. This is the PID of the customer tracker server. To verify, you can also call the dynamic.waitChildren function just to verify if the PID matches or if the PID is that of a child process. So you could see the worker that has been started under the dynamic supervisor is the customer tracker server. From there, you can interact with your GenServer process, which has been started on demand using the dynamic supervisor. For example, we have the PID. Okay, let me just redefine this. Usually, it's best to pattern match if you want to get hold of the PID. 350. Okay, so that's the PID of the customer tracker. We have some of the custom function that was defined here. So we have already started. Let's say we want to add a customer. To add a customer, we pass in the request as a tuple. I had this function here to raise an intentional error. I need to close this. Let's see if I can recompile and fix it up. Okay, let's add a customer here. So add customer. I'll call this function customer tracker. Add or remove customer, pass it the PID, then pass it the request. So the request is add customer and the number of customers that we want to pass. So that is add customers. Let's say we're adding 3 customers. Key error, customers not found. Yeah, and I have an error ready. Good. The GenServer process, our customer tracker server has been started with initial state of an empty list. So that's why it's raising a key error suggesting that the key customer is not found in an empty list. How has this happened? Remember how we have start our child process? When calling the dynamic supervisor startLink function, we have passed the registered name of our dynamic supervisor, and we have passed the module name of the customer tracker server. So with that, by default, it's going to take an empty list as the initial argument. So let's change that. If we want, you can always tell the dynamic supervisor how to start your child process using the start option, but we're not going to go through that route at the moment. Okay, so let's restart the customer tracker. So I'm going to call the startLink function again. I'm sure that this process is not alive at the moment, so we'll have to restart it, but let's confirm. Yeah, it's not alive, so let's restart it. Each time I want to clear this with the VS Code, I used the command K option, but now here it's Control L. I have to keep reminding myself this. Okay, so let's clear. Okay, not clearing again. So I'll use clear. We have to restart our customer tracker under the dynamic supervisor. I want to pattern match this with an OK PID so that we don't have to use the PID kernel each time we want to access the PID. We already know that this function returns an OK, a tuple of an OK PID, and the PID here is the PID of the child process that is started under the dynamic supervisor. Also, I'm going to define the child specification using a tuple and now pass the initial argument. I'll copy this because when we call the startLink function, we wanted this to be the default argument, which is the initial state. I'll start that. We have already started our customer tracker server. Now let's interact with it. Let's add or remove customer tracker. We have a customer tracker and we're going to add or remove. Pass it the PID and the request, that is a tuple of add customers and the number of customers to be added. Let's pass 3. And now it has worked. Do we say hooray? Okay, let's get the number of customers. That is the PID. And the request, I have to check which request is being handled when getting the number of customers. Or do I have? Yeah, so get customer number. Hooray. We have current customers number is 3 and the time that they were added is this. That's a win. How do you celebrate your wins? Because this is a good feeling when everything gets to work. That is a basic example of how Dynamic Supervisor works. In this case, we have used an inbuilt Dynamic Supervisor. Similar to the module-based supervisor, you can also define your own Dynamic Supervisor. So I will share the link to the documentation so that you can explore more on it. Dynamic Supervisor comes in handy when you want to start the child processes on demand. Let's say you are handling a payment system and you want to start a process for each transaction that comes in. In this case, the Dynamic Supervisor will be a better option for dynamically starting these processes. However, it can also be dangerous to your application if you are not careful. Remember, each process that is being started is consuming a memory. And if you're dynamically starting a process for each transaction, that means more memory will be required. So if you're not careful, this might have an impact on your application performance. How do you handle a case like this? In a real case scenario, most of the time, this process gets to be terminated once they complete the job, so that you don't have an idle process that is running and consuming the memory unnecessarily. Like our customer tracker, we can stop the GenServer once it has completed its job. In today's session, we shall be exploring the PartitionSupervisor. So far, we have covered the model-based supervisor and the dynamic supervisor and understand how each of them can be used to manage processes. So what is a PartitionSupervisor and how does it work? Imagine you're just opening a new restaurant, and since in the first few months you're not expecting that much traffic of customers, you decide to only hire one waiter and one chef who will handle the customers. So when a customer comes into your restaurant, they place their order, and in like 10 to 20 minutes, their food is ready and they leave that place happy. After a while, more customers start showing up, but still the restaurant has that one chef and one waiter who are operating. Food is served on request, one order at a time, and each customer has to wait for their turn. With fewer customers, the restaurant was easy to operate. Now that the traffic has increased, the service starts to slow down. This is a great analogy of what happens with software system as they scale. With time, this software system can also struggle to keep up with the increase in demand. And this is what we term as bottleneck. Look at a bottleneck as a factor that slows down the system or prevents it from running efficiently. Bottleneck can be brought about by many factors. It could be as a result of a slow database query, or maybe limited hardware resources, like not having enough memory space, or even your code architecture. Going back to our restaurant, it's now having more traffic of customers. The bottleneck in this restaurant is the staff, because it only has one chef and one waiter. With the increased number of customers, there's that kind of frustration that is being created because of the slow operation or the much time that it takes to serve the 6th or the 10th customer within that restaurant. If it was 1 or 2 customers, it was easier because for each meal to be ready, it takes 10 minutes. So by the time you reach to the 2nd customer, that is 20 minutes. But by the time you reach to the 10th customer, that is like 200 minutes for this customer. You as a customer, you definitely feel the pinch. The tools that we introduce to our software system at some point, they can also become a bottleneck. And a very good example here is the DynamicSupervisor. Probably you are wondering, how is the DynamicSupervisor a bottleneck? Yes, DynamicSupervisor is a very important tool. They help in starting a process on demand and also under supervisor. But now, how is it a bottleneck? Let's look at it. We had already done a session on the DynamicSupervisor. In case you missed the video, check the description below. When working with the DynamicSupervisor, we started a child process on demand. However, the DynamicSupervisor can only start one child process at a time. Just like in our restaurant scenario where we have one chef and one waiter and meal are prepared on demand, that is when a customer makes an order. So in this case, the chef can only prepare one meal at a time for that order, and the waiter can only handle one customer at a time. In the previous session on DynamicSupervisor, we were starting the customer tracker process on demand. If we are making 1 or 2 requests to start the customer tracker on demand to get the information, everything will feel smooth and fast. Now, imagine we are making more than 10 requests to start the customer tracker process, and each request has a gap of like 1 second. For each request, let's say it takes 5 seconds for the customer tracker process to be initialized. Can you now guess where the problem is with the DynamicSupervisor? Earlier on, I mentioned the DynamicSupervisor can only start one process at a time. And when starting a process using the DynamicSupervisor must wait for each process to be initialized before moving to the next. Again, picture this with the restaurant scenario. A chef receives an order and they start preparing. So at the point where they're only waiting for the meal to be fully boiled, then serve it, it's when they can move to the next meal. But at the point where they have to chop, they have to put oil and all that, they still have to focus on that one meal before moving to the second order. Let's go ahead and simulate the bottleneck brought about by the DynamicSupervisor. To demonstrate this, we are going to delay the initialization process of the customer tracker server by 5 seconds. To delay the initialization process, let's add process.sleep at the init callback and give it 5000 millisecond, which is 5 seconds. Also, let's print a statement so that we know which process has been started. I have also customer tracker initialized with name. So this will be representing the name of the process that has been started. This name is being fetched from the state, and also each process that you are going to start will be uniquely registered by its own name. To register a process, you have to pass the name option at the startLink function when calling GenServer.startLink. So this name will be extracted from the option that we pass when you start the process. The changes that we have made is enough for us to simulate the bottleneck. Let's go ahead now and start the interactive shell. To do that, I will run the ix-s mix command. Okay, and now we are ready to start our process. To demonstrate the bottleneck, we are going to use the DynamicSupervisor to start 5 processes that will be responsible for tracking the customer information. I want us to start 5 processes, and I'm thinking of adding a helper function than writing the whole logic in the interactive shell. Let's first add that helper function. Okay, so I'll just use the customer tracker server to add the helper function. There is not a recommended approach. This is for demonstration purpose. Let me just add it here, up here. I'll define a function. Let's call it tracker servers. It will not take any argument. Then I need a list of the servers. So let's call them server names. I think Cursor is doing a very good job of auto completing for me. So give it customer tracker server 1 and I will add 2 more to it. We have that. Then I want to iterate through those server names and start the process dynamically. I'm not using the output, so enum each is just okay, which returns an okay once it has completed. So give it the server names. I don't want this, please cursor. Dynamic supervisor start child, I want that. Then remember our option here is a map. So I'll copy this and replace what cursor is suggesting for me and I don't want. So we have the customers. It will start with the 0 customers, or let's just put it as 1. That time the names, replace this with the server name. I'm passing the server name as an atom because atom is one of the supported values of how you can register your GenServer process. There are other 2 different ways of how you can pass the name of a process. I'll share the link to the documentation. Another thing we need to add is a spawn function, and this is because with enum they perform tasks sequentially. I want this logic to be performed concurrently. Let's add a spawn function, sorry. So just remove this. It takes in an anonymous function, then add the task that needs to be done and close this. Yeah, now we are ready to test this logic. So let's see how it works. Recompile the changes and call the tracker server. I'll clear this first. So this is an output of the enum each, and you can see we are getting the print information after every 5 seconds. So the DynamicSupervisor has completed initializing each process that had to be started. Let's also try to use in a map to get the feel of what is happening inside this tracker servers function. I'll replace the enum each with enum map. The logic is just the same. We are iterating through the server name and to start the process dynamically. It's just that with enum each it returns an atom okay, but with enum map we are expecting a list, and we're expecting a list of PIDs that will be returned by the spawn function. I had closed my interactive shell, so let me restart it again. Then call the tracker servers function, and you can see it immediately returns a list of PIDs. So this means that the task that is happening here is happening concurrently. It's concurrently calling the DynamicSupervisor start child to start the processes dynamically. And from here, once the start child is called to start a process, you can see that we are getting the print information after every 5 seconds. So this here is a proof that the DynamicSupervisor is initializing a process sequentially. We have seen that the DynamicSupervisor starts the processes sequentially. In our demo, we are only starting 5 processes dynamically, and the initialization process has been delayed with only 5 seconds. Definitely with this, you won't feel the pinch. But now imagine you're having an application that is handling more than 1,000 requests in a day, and for each incoming request you are starting processes dynamically. That is not even the problem. The problem is that at the initialization stage you have a heavy workload that must be performed before that process is initialized. Knowing that the DynamicSupervisor handles requests sequentially, I started to understand how you can easily introduce a bottleneck to your application. If you're using GenServer, avoid performing heavy tasks at the init callback. Instead, prefer using the handle continue callback for the post initialization work, unless there is need to. Back to our restaurant. For the restaurant to keep up with more customers, it definitely has to increase the manpower. With the increase of manpower, the more waiters and the more chefs, they will be able to distribute the workload involved when more customers keep showing up. We have seen how the dynamic supervisor work, and if your application is receiving more requests and you're relying on the dynamic supervisor to start a process for each request, it can be a problem. How can you distribute this workload so that the dynamic supervisor doesn't be a bottleneck in your application? This is where the partition supervisor comes in handy. With partition supervisor, you don't have to rely on a single dynamic supervisor to start all the child processes. How the partition supervisor works is that it's able to start multiple instances of the dynamic supervisor, each on its own partition. By default, the number of partitions created depends on the available cores in your machine. If you have 2 cores in your machine, that means 2 partitions will be created. If you have 10 cores, that means 10 partitions will be created. To confirm the number of cores that you have in a machine, you can use the system scheduler's online function. The number of partitions can also be overridden when defining your partition supervisor by passing the partition option. So don't be worried if you have less cores. That will be the final number of partitions that will be used. Enough of the theory. Now let's see how the partition supervisor works. So I want us to implement a partition supervisor, and we shall follow the example provided on the partition supervisor documentation under the dynamic supervisor example. Let's jump straight into it. This is a dynamic supervisor example. We are told that dynamic supervisor is a single process responsible for starting other processes. In some application, the dynamic supervisor may become a bottleneck, just the way I had explained earlier. So to address this, you can start multiple instances of the dynamic supervisor through a partition supervisor, and then pick a random instance to start the child on. So further on, instead of starting a single dynamic supervisor, so for a dynamic supervisor to be started, you have to pass it under the children in your application and starting children on that dynamic supervisor directly. On our previous session, you had seen how we were starting a child process dynamically using the dynamic supervisor. So instead of that, you can start the dynamic supervisor under a partition. And this is what we want to do, to start a dynamic supervisor under a partition supervisor. So we shall copy this example as it is. So already have children list defined. So I'll just copy what is inside here. When your application is being started, it will start the partition supervisor as its child. So let's copy this and add it. Now we shall comment this out because we don't want to start a single dynamic supervisor, but rather start instances of dynamic supervisor under the partition supervisor. We'll comment that out and paste this here. This is under a children list. We have a partition. The child spec is dynamic supervisor. This will remain as it is. We are replacing my app dynamic with the gen demo dynamic supervisor. So with the configuration or with the setup that we have just added in the application file, when our application is started, the partition supervisor is going to be started, which by default is going to start the dynamic supervisor. So in this case, the gen demo dynamic supervisor. So remember, it's going to start multiple instances of the dynamic supervisor depending with the number of cores you have in your machine. Let's see how many cores I have in my machine, which determines the number of partitions to be created. I don't want to start the application yet, so I'll just use the IEX. The function that gets the number of cores is called the system. So I use the system scheduler's online function. I have 10 cores in my machine. That means by default, 10 partitions will be created. You can override this number by adding the partition option. You can just add partition. So instead of 10, you can pass 20 or you can also decide to reduce depending with their needs. So I'll remove this because 10 is enough. I don't want to increase or reduce the number. After setting up our partition in the application, now we want to start the child process through the partition supervisor. Previously, we were calling DynamicSupervisor start child, and the first argument we are passing to it was the GenDemo DynamicSupervisor. We need to refactor this by following the same format that is given in the example. To start the child process through the partition, we need to pass this routing key with this format. So therefore, I will copy this and replace the GenDemo DynamicSupervisor with the format that is required now. Let's go ahead and replace the name and the key in the routing request that we have just passed. The name here is the GenDemo DynamicSupervisor. So this is the name of the DynamicSupervisor. The key represents the routing key. So the routing key is the one directing to the dynamic instance that needs to start the child. Replace the name with the GenDemo DynamicSupervisor. The key can be passed as an integer or as a PID. For the partition supervisor to determine to which instance to route to, there are two routing strategies that are used, which are determined by how you pass the key, either as an integer or a PID. If you decide to pass the key as an integer, this is the routing strategy being used. So this is a rem function which takes in the absolute of the key and the number of partition. So let's see what will be the routing instance when we pass it as a key. So just use this interactive shell here and paste it. Let's guess of a random integer, 2 for instance. The number of partitions we saw is 10, so I'll just pass 10. So the instance being used will be 2. What if I had 8 partition? The same 2. What if I had 2 partition? None of the instance. What if I had 1 partition? Still 0. What if I had 20 partitions? The instance being used will be 2. Another routing strategy used when you decide to use a PID is this along function, the first 2. Let's copy this and see to which instance we shall be routed to if we give it a PID. So I'll paste this here. I will give it the PID of the interactive shell that we are currently working on. This is the PID of the interactive shell. The number of partition, I'll start with 10. So the instance I'm directed to is 9. What if I had 2 partition? I'll be redirected to the first instance. What if I had 1 partition? None. What if I had 50 partitions? So this is the instance that it will take me to. In the documentation example, they have passed self as the routing key. Let's do the same thing. Okay, so let's replace this with the self. Also, I just want to know what are the instances that our process will be assigned to. So therefore, instead of passing, I'll create a variable for self, then pass this as PID. Also, let's inspect this by passing PID. We already know the number of partitions that we have. That is 10 partition. But just to be clear, let me just pass system. Let me define system.schedule as online function. And we inspect this. I'll name it routing instance. Okay, and I think that's it. We are now ready to spin up the server and run the tracker server and see if we are able to avoid or eliminate the bottleneck that we faced earlier. Okay, to start the application, run the ix-smix command. So this way the partition supervisor will be started, and also it will start the DynamicSupervisor instances. Let me just clear this. Now we can start our customer tracker server and see what happens. You can see routing instance this PID. The routing instance is 3, and if you notice, it's behaving the same way as it was while we were just using a single dynamic supervisor. So why is this the case? Are we not solving the problem with partition supervisor? So I've just realized where the problem is. We are routing to one instance of the dynamic supervisor, and this is because of how we're using the PID. The process here is of the tracker server process, which is not changing, and each time we are routing to one instance. I'm thinking for a request to be routed to different instance of the dynamic supervisor, we need to use different kind of PIDs. At the moment, I'm not sure of how I can generate different PIDs. Let's switch from using the PID to using keys. I think that will be much easier for our demo. What I'm thinking is we can refactor the server name to have a list of tuples. Each tuple will have the server name and a key ID, which is an integer number. Let me just refactor that. So we have that as the server name. I'm removing the PID. Definitely I will need to use the inspect. Instead of removing it, I'll just cut and paste it in here. I need to change this because the routing strategy has changed from that to using the rem function. The rem function takes in an absolute over key, then the number of partition or the number of cores the system has. This is server name. Now I need to pattern match with the server name and the key. So I have that. I'll change this also to key. So now we're not passing the PID, but we're passing the key. I think that's it. So we can recompile. Let me just start the server and run the ix-smix command again. Now let's see what's the behavior like. So we have 5 different instances that has been started, and you can see that we instantly or immediately received the result of the printing that we added. Each of the instance took 5 seconds to start the child, to initialize the child process. With this demo, you could see here that we have like a distributed workload. So each instance had its responsibility of starting the child process, and compared to how initially it worked with the dynamic supervisor, we had to wait for one child to be initialized at a time. That's it for this session. We have seen how the dynamic supervisor can be a bottleneck to your application, and also how you can use the partition supervisor to avoid this bottleneck and handle concurrency more effectively. On today's session, we shall focus on name registering of processes with dynamic names using registry. There are some places when you visit, usually the security guard has to write down your details maybe in a book before you are given access to the building. For every visitor who wants access to the building has to go through the same process. For manual process where details has to be entered into a book, it will definitely result into piles of book accumulating. So far, we have been registering our GenServer process using atoms. One thing you should know with atoms, they are not garbage collected. Garbage collection is a memory management process where a memory is usually reclaimed from the objects that are no longer in use. Imagine a scenario where you want to register processes dynamically. This will definitely be risky when using atoms, knowing very well that they are not garbage collected. Let me give you an example. You have an application which handles checkout. For every user that performs a checkout, a new process is created. This process will be dynamically registered with an atom name. In such cases, usually you don't have a control over how many atoms will be created. This is because you don't know how many times one user can perform the checkout process, and also you don't know how many users will interact with the checkout. Over time, this will definitely lead to excessive memory usage of your application. In Elixir documentation, it's clearly stated if there's an interest in registering dynamic names locally, do not use atoms, as atoms are never garbage collected, and therefore dynamically generated atoms won't be garbage collected. For such cases, you can set up your own local registry by using the registry. Registry in Elixir is a key value process storage. So once you store your process in a registry, you are able to look up for that process using the key that you assigned to it. So since we are dynamically starting our customer tracker server using DynamicSupervisor, we can now switch from registering our process with Atom to using registry. We can go ahead now and configure a registry that will be responsible for all the process that will be dynamically started. There are two ways we can go about this. First, it's either to start the registry as the child of the main supervisor of the application, or we can call the registry start link function that will start the registry. Let's pass it as a child of the main supervisor. We'll add it here in the list of children. That will be registry. You have to specify the keys. If the key should be unique or a duplicate, you can decide to register processes with duplicate names, or you can decide to register process with unique names. So let's use unique. Then you have to pass the name. So this is the name of the registry. Let's call it the customer tracker registry. Yeah, we can have it as the customer tracker registry. Next, we shall specify how we want to register the GenServer process using the VIA. This is the format that will be used, the VIA format that will be used. So we need this registry. Then this replaces with the registry name that we are using. And our registry name is the customer tracker registry. Then this specifies the name that you want to use. So here we have passed the name of the registry, and also we need to pass the name. So the name is the one that we are getting from the options. The options is the one that was containing the name key. Now I want to pass this as a string instead of an atom, and then this can remain as it was. So options. The other thing I want to change is the server name. So here we were passing the server name as an atom. Let's change this to string. So this, instead of an atom, let's pass it as a string. Okay, so now we are ready. So let's spin up the server and start the processes. So that is ix-smix command. So we are calling the customer tracker server. The function is tracker server. So this is the function which I'm calling the tracker servers. If you recall well, in this tracker server function, we were dynamically starting the GenServer process. So let's call the tracker server, and we have 5 processes which are dynamically started. We have 5 processes which are dynamically started, and they're all registered with different names that we passed. I want us to check the PIDs that will be returned with the name that we have registered the process with. So we shall use the GenServer where is function, which takes in the name of the process. So remember, we have a different server name that we registered our process with. We can pick 2 of the names. So this is how we are naming our GenServer. So first, let's copy this. Create a variable, maybe name 1. So definitely options is not defined. Let's create a variable name 1. And we have the name of our server. So I had closed this. Also, let's create another variable, name 2. Then call the GenServer where is function and pass it the first name. and you see we have this PID. Then call it with the second name, it will give you a different PID. So we have two different PIDs. So these are two different processes that have been started with different names. The other way that you can use to check the PIDs, the processes that has been started. So let's look at the processes stored in registry using the registry lookup function. So call the registry.lookup and give it the name of the registry. So the name of the registry is the one that you had configured with. I'll copy this and also give it the name of the process. So the name of the process is this. Now we are not using the whole var, but only the name that you had passed in the var. So you can see this PID is matching with this. Remember, a registry is a key value process storage. If you look up for that process, it's returning the process and another value as nil. So this is because we did not pass a value for the process. So the key is the PID. Let's do the same for the second process. You'll see its PID is matching with what we had for the name2 variable. So we have configured our registry as a child of the application main supervisor. Another way you can start a registry is by using the registry start link function. That is, just call the registry, the start link function, pass the keys. Remember, you can pass it as unique or as a duplicate, and also give it a name. We already have a registry, so we named it customer tracker registry. For this, let's name it another registry. This is another registry that has been started. Let's see what happens if we give it an existing registry. So that was customer tracker registry. You're told that it's already started, and yes, it was started once we started our application. That's it for this session. We have seen why atoms are not good for registering your GenServer process, more so if you're using dynamic names. And if you're using dynamic names to register your process, prefer using registry. As usual, if you found this video helpful, give it a thumbs up and don't forget to follow for more Elixir tutorials.